the adjustment. Anyway, okay. I can just hear my voice too much. Anyway, thanks a lot for inviting me, Tim, and all the other organizers. Really nice to be here. So I changed the title a little bit, as you may have noticed from the abstract. I mentioned some experiments as well, but then I realized, well, first, what I will tell will be too long anyway, so I will not have time for the experiment. And my gut feeling is that this audience is maybe less interested in the experiments anyway. No offense. But I do have some slides about an experiment that is actually related to deconfined criticality. So, if somebody asks me, at the end, I can talk a little bit about that. Okay, so deconfined criticality, that has to do with this phase transition between the familiar male antiferromagnet and the valence bond solid. So that has been sort of a long story developing over many years, and I'm going to talk about that. These are my main collaborators during the past few years. I have other collaborators that have become apparent in some papers. So Hui Xiao and Wenan Guo, they're from Beijing Normal University. John Demedio is in Spain currently, and Jun Takahashi was a postdoc when I spent some time in Beijing. Now he's a postdoc in New Mexico. But actually, before I get to all this, I want to give an extensive introduction, because I think here most people are maybe from the particle physics field theory community, which is a little bit different from myself and from the condensed matter numerical community. So there may be some difficulties in communicating, which I hope to overcome here. So let me present the setting of what I'm going to talk about in more broad terms first. So what I do is basically numerical studies of quantum lattice models, sometimes also classical models. So mainly I use quantum Monte Carlo methods, so we can study, we study finite size systems, we can study ground states of those, or we can study finite temperature properties as well. And of course, we want to make, big lattices, so we use a lot of compute time to do that. So my particular interests most of the time would be to study some non-trivial ground states and the quantum phase transitions between those. Okay, so as I mentioned, sometimes we do classical simulations as well. Both because they are often a little bit simpler, so we can use them to get some insights and learn how to do things and benchmarking and so on. But in both the classical and quantum case, of course, we can have phase transitions as a function of the temperature or some parameter in the Hamiltonian, and we can have continuous or first order transitions. So in the quantum case, what I have in mind is zero temperature, and the Hamiltonian has sort of two parts. Actually, there should be a little a in front of this one. So we tune the ratio of those two terms to change the nature of the quantum fluctuations and get transitions. Okay. So of course, in this case, we have a divergent correlation length, and in that case, the correlation length doesn't diverge. Okay. So what is the aim of my lecture here? Well, so I would like to talk about how to, when we do simulations, and by the way, I will not talk about any technicalities about, how we actually do the simulations. I will just talk about how we analyze results and try to get something useful out of those. So what I want to do is basically, and what I try to do in my research is to connect results to what you guys doing field theory are more familiar with. So try to connect the two communities in the sense of we study some low energy phenomena in those models, and they are described in principle by some field theory where people can do RG and so on. So we want to connect to that field as well. So I think the sort of connection, the bridge between those is really the scaling dimensions, which we can compute numerically and which field theorists are familiar with, and it's important to in the field theories, of course. So what we do is we do finite size scaling. So L is a variable, and we change L, and as well define ways to extract scaling dimensions, or what we often in the condensed matter community we talk about critical exponents, but of course they are related to scaling dimensions. Sometimes we can also look at really big system sizes and look at correlation lengths, correlation functions as a function of the distance, and get the scaling dimensions from there. Okay, so about these lectures. So the first part really will be an introduction, and I will not talk about deconfined criticality at all. I will talk about things that have some parallels in what I will talk about later on in the context of deconfined criticality, just to sort of fix the language barrier maybe. And then part 2 will really be about deconfined criticality. So I think it will be pretty much 50-50 each of these, so we can have a short break in between. Okay, so let me talk about the starting point for many of the studies we do, which also is in some sense the starting point for deconfined quantum criticality, the 2D Heisenberg model. So we have spin on half, and we have a square lattice typically, and this is the Hamiltonian, and I guess most people would have seen this before. So here the order parameter is the sublattice magnetization, right? We have a checkerboard sort of pattern of ordering, if we do have ordering, right? So if we numerically want to study this model, we study the squared order parameter and see if it goes to 0 to a finite value as the system size goes to infinity. And by the way, everybody now knows that this model has long-range order in the ground state, but there's no analytical proof for s equals 1/2. There is analytical proof for s equals 1 and higher, but not for s equals 1/2. And maybe those of you who are old enough would remember that Phil Anderson at some point in the end of the 1980s proposed that this model would actually be a spin liquid. It would not have any long-range order, but numerics show that it does have long-range order.
Question?
Yeah.
What was the analytical proof for high-res due-to?
Actually, I don't know, or I don't remember. I think I at some point long ago looked at the paper, but I don't. It's an old thing from the probably early 90s or something like that. Yeah, but I don't know. Some mathematical physicist, I'm pretty sure.
Anders, good question. So, I mean, it's known from numerics for the square lattice. What about for triangular lattices?
Yeah, so for triangular lattice, it is also ordered, but there's not a staggered order. There's if you look at the triangle, 120-degree shift.
But I thought that has a sign problem.
That has a sign problem, but people have done DMRG
and they're quite confident that's the phase?
Yes, there's no doubt anymore. Yeah, so that was, of course, the original model in which Phil Anderson proposed the resonating valence bond spin liquid state, but actually it's also in that case it turns out not to be the case. Okay, let me just show some example of how we can know numerically that this model has long-range order. So I will show some results of quantum Monte Carlo, which, by the way, for a given finite size, we can really say that the result is exact to within some statistical errors that can be very small. But we have to do an extrapolation to infinite size. So this was done in a sort of believable way, already a long time ago, 1988, and they got this value 0.3. So if you think spin 1/2, classically, the max value would be a half. So it's actually a pretty robust long-range order. Now, what we can do these days, well, I show some results that are already, quite old, so we could do even better now. But now we have this kind of number here. And how do we get that? Well, using very big system sizes, and again in simulations where we are confident that we can take the limit of the temperature going to 0. we can actually do two types of simulations. One type is a finite T and we let the temperature go very, very low. The other kind is projector QMC where we start with some what we can call trial state and we project out the ground state. But in the end it's quite similar. So this is actually from projector QMC. So what I showed here, these dots, they are as a function of the inverse system size. One is exactly this order parameter m squared as I showed there, although I use a slightly different symbol. And the other set of points is from the correlation function at the longest distance, which should also go to m squared if there is long range order. And then, analytically, from the fact that there's, gapless, goldstone modes here, one knows that the leading size correction should be like 1 over L, and then there should be higher order polynomial corrections. And you can see that such polynomial fits work really well, and that's how we get this result. Okay, so that's one sort of thing that will be useful when I talk about deconfined criticality eventually.
Sorry, can you just say, what is this MS 0.3? What does that mean? Okay,
so that means the value of the order parameter, you have spin rotation invariance, spin rotation invariance here, right? But once you break the symmetry, let's say in the z direction, if you measure the mean value of the spin Sz, it will be 0.3.
Okay.
If it would be a classical, model with, vector spin length 1/2, you would get 1/2, right?
Okay.
That's what it means. So the maximum, if you take Ising model,
but you mean measuring ms squared and then taking the square root of 1?
Yeah, exactly. Because I mentioned it here because we don't actually break the symmetry on the finite lattices, so we have to compute m squared, right? Okay.
But you could also compute the absolute value.
Say again?
You could compute the absolute value of ms.
Yeah, you could do that. Absolutely. Yeah, that would give the same thing. Yeah, we have done that. Good. Okay, let me talk about how to analyze phase transitions because the previous case was just showing that a system with a non-trivial ground state, although it's sort of a classical type ground state, is how to do that. Okay, let's look at just classical phase transitions. So we know that we have a correlation length that diverges as we approach the critical point. And if you look at some other quantity like the order parameter or whatever, you can write it as some power of the correlation length. So here kappa would depend on what quantity you look at. So order parameter, specific heat, whatever. So now if we, instead of having an infinite lattice where this can really diverge, we have a finite lattice, then the correlation length just stops at L. So then we just replace this by L, and we see how we expect if we are close to the critical point, and closeness can be very well characterized as well. There's this power law decay with the exponent kappa over nu. So, and in fact, one can go further and say, okay, so if you go a little bit away. And this, by the way, was first written down as a hypothesis long time ago, and later on it has been shown in RG that this is the case. That it should actually be this overall L power times the function of the ratio of the two length scales of the problem, right? And then you can take the power of that and write it in this form. And actually, when you write it in this form, then this function is analytic for x going to 0. If you write it in this form, it's not an analytic function, but in this form, it's supposed to be. So let me show you some examples of this from the 2D Ising model, I guess everybody's familiar with. So here we know these exponents. So if we do simulations for different system sizes and look at some quantity, in this case, I look at the susceptibility, the magnetic susceptibility. So this exponent kappa is minus gamma because the susceptibility diverges, right? So this has to be negative. And we know the value of that exponent. Okay, you can see as we increase the system size, this peak gets sharper and it shifts a little bit, and the shift one can understand from the scaling function. But let's see now if we actually know the critical TC as well from one-sided solution. So this is a case where we can really test it very easily. If I replot the same data now where this overall factor is multiplied multiply out so that I just get the scaling function and then I plot as a function of that scaling argument. You see, I get data collapse. So if the system size is big enough, this will fall on a single curve, which is the scaling function. But of course, there's some corrections on top of that. So for small sizes, it doesn't quite fall on top.
So if this was actually a first order function, these curves wouldn't fall on the top of each other. This is how you would distinguish.
Well, I think they would probably still fall on top of each other actually, but the exponents would be some sort of trivial exponent. Like the exponent u would be 1 over d being the dimensionality and things like that. So actually, if you analyze the first order transition numerically, it still actually looks like the correlation length diverges. So what I said before, that the correlation length is finite at the first order transition. That's if you look at it in a way where you really break the symmetry from the ordered side and so on. In simulations, you will actually have coexistence at the transition, and that will lead to something like a divergence in some definitions of the correlation length. So you can do the same things, but you will get some, basically, let's say, trivial values of the exponents. Yeah.
Related to these comments about first-order phase transitions, do you basically mean that near a first-order phase transition with at least simple update algorithms, you'll get supercritical slowing down?
Oh yeah, that's another thing. It becomes very, very hard to actually study the first-order transition, and that's exactly because you have phase coexistence. So the system would like to, swap between two completely different states, right? And that takes very long. So that's a good point.
There's a sampling algorithm that can handle this.
Well, there are some algorithms that can handle it, but it's still actually not easy. I mean, one lambda sampling, whatever, things like that. But yeah, I don't really want to get into too much. We can discuss after for sure, but I don't want to get into really technicalities of simulations because it would take too long. Anyway, so this is the basics of finite size scaling. Let me mention a quantity which is quite useful. Well, as I mentioned here, if you don't know, the exponent and the critical point and so on, then you would, take these exponents as parameters and adjust them until you do get scaling collapse. That's one way to do this data collapse and extract the exponents, but actually it's not the best way. So let me tell you about some better ways to get TC as well as exponents. So the Binder ratio is a nice quantity because it's a dimensionless quantity. It's the ratio of 1 power of the order parameter divided by half of that power, but squaring it after. So if you look at in a simulation, this is from the Ising model. If you look at the distribution of the magnetization in a simulation, you will see that if you are above TC, you just get a bump at around 0. Okay, and if you increase the system size, the bump just gets stronger and you get Gaussian fluctuations, so eventually this becomes a perfect Gaussian. If you are below TC, you have 2 peaks, and symmetry breaking means that, well, these peaks become so sharp for large system sizes that you just get locked in there. You cannot tunnel between them. Okay, so let's look at the Binder cumulant. So you can easily see from this kind of thing in the limit of large system size where these become delta functions that this Binder cumulant goes to 1. Whereas if you look at high temperatures, then this becomes a Gaussian, so then you can also compute it, and this, in the case of the Ising model, this goes to the value 3. This was, yeah.
So the numerator is the connected.
Say again?
The numerator is the connected correlation function, right?
No, so this is just the magnet. Well, okay, so it depends. Yeah, good point. In this case, there's nothing to subtract in the connected one because the average is 0 anyway. Sometimes you have to be careful and maybe there's something you have to subtract. But in this case, since the mean value of m is 0, you see that from the symmetry of this.
But the numerator is not m4 minus 3 m squared.
No,
squared.
no.
Okay.
No.
It's a one-point function.
I mean, you could probably.
Otherwise, in the broken phase, wouldn't be 1.
Right.
And when you say it's known exactly for n, so what is n here? N is
Okay, so this was what I was going to say. So this is a one component order parameter. You can imagine if you go to more components, you have to do Gaussian integration in higher dimensions and so on. So if you want something, well, so this was the ratio. So what you normally do is you want something that's 0 in the disordered phase and 1 in the ordered phase. And then this is what you should do to do that. And it just follows from Gaussian integration when you have components. Okay. So an example of that again, the 2D icing model. You see here that this, for increasing system size, this develops a step function, and an interesting property, and this is quite general for many models, because this is a dimensionless quantity. There will be size independence at the critical point, and normally the size independence is reflected in a crossing of these curves for different system sizes, which you see happens here. So TC is where those cross. Now this looks really good, like wow, they're really crossing one point, but actually, blow it up a little bit. This is actually another set of calculations, but it's the same thing. You see, if I really blow up close to TC, you see that the crossing points actually shift. So then one has to extrapolate to infinite size, and one convenient way to do that is to consider system sizes L and 2L, and then from the expected critical form of this dimensionless quantity, we can get points as a function of 1 over L. And you see that they do drift, and eventually, this should be a power law governed by, the leading scaling correction, basically. And you can also look at the value of mu itself. So this is one way to extract the critical point. And so this is, from this form and doing some Taylor expansions and so on, you can see that this is the way this approach the critical point. Yeah.
So the reason to always go 2L?
You don't have to go 2L. This was just example. You could do L and L plus constant or something like that. But yeah, often we use L 2L.
What are you exactly extracting? Are you extracting corrections omega 1, omega 2?
Well, so in doing this, the goal would be really to extract TC. You do get some estimate for this exponent as well, but there are better ways to actually get those exponents, because everything is, correct. Let me mention here. You see here I fitted a power law, just a single power law, and it doesn't really fit, the small system data. So what you can do is to exclude small sizes until it sort of works, until statistically good. That means that the effect of the higher order corrections are small.
Did I get this correct? T star, you use 2 points, for
That's
example,
right.
L and 2L.
That's right.
And where they cross, this is your T star.
Exactly. Exactly. Yeah. So you do get, if you fit that power law, well, that should ideally be given by that, but there's always some effect of these higher order corrections too. You can imagine, and these are all, scaling dimensions from filter, and I will discuss a little bit more about that, but there's always some sort of little error that you still may make. But let's look at this case. TC, this is TC from this calculation here, where L minimum was 12, which is where it starts to work, and this is the actual TC. So with statistical error, it actually agrees to some horrendous accuracy. Now this is actually too good to be true, in the sense that the icing model is so. Oops, I thought I had another statement here. The icing model has such small scaling corrections, meaning that this exponent is so large that it just looks very good. So when people see things like that or learn it from this, then they sort of get spoiled. And then when we go to other cases, which I will hopefully have time to talk about, it looks strange because people are not used to cases where there are more corrections.
Is it understood why it has such small?
Well, yeah, in the sense that people know from conformal field theory everything about the scaling dimensions of the 2D icing model, and these are not exactly coming from that. I will say a little bit more about that. So understood in the sense that if you know the low energy field theory and compute all the You know the exponents, but of course you don't know the amplitudes of the corrections. I don't think.
Right.
Can you fine-tune your observable to kill the amplitude?
Yeah, you can also do that. Yeah, but then everything you do takes computer time. So sometimes we cannot play around with infinite perfection.
Could I ask a question about the dimensionlessness of the bin accumulate? Is there some assumption that there's no anomalous dimension there, or
No, I don't think so. I mean, I think for any sort of, yeah. So I guess it's a good question at some point. Think about that myself. Is it clear that this has?
Yeah, it clearly works.
It's not about the anomalous dimension. If by that you mean the exponent eta.
Right.
No, it's not, because this has an anomalous.
Yeah, exactly.
It cancels out.
So
It cancels out.
I think that as far as my understanding, these distributions of criticality, they are not universal, but the cumulants of the distributions always scale. If you take a power 2, you get 2 times the scaling dimension and so on.
Okay.
Yeah.
Okay, thank you.
I think that nobody will dispute that, but yeah.
There is only one exception, which is if the scaling dimension is very high, then some of these functions can be dominated by the short distance.
Then you need to go to extremely large system sizes. I think that's what.
The critical point, this notation means some kind of integrated 4-point function.
Yes.
And you have to worry about that this even converges. I don't know.
Yeah, I don't know. I mean, maybe there are some subtleties here, but I have never seen any case where this wouldn't work. We can discuss after, maybe there's something interesting there. So let me tell you how we can get this correlation length exponent in some measures. This is the scaling form I already showed you. Now, if you take the derivative of this scaling, so this was when I got rid of this overall power here. Let's take the derivative, then we get that form. So then if we evaluate the derivative at the critical point, then that should scale as L to 1 over nu. So in the case of the bin accumulant, we don't even have to multiply anything because it's dimensionless. And then again, this is for the Ising model. Just looking at the slope of these bin accumulants, the slopes of these at the critical point. Actually, there's also a maximum in the slope, so you can even just look at the maximum, which doesn't necessarily occur at TC for small systems, but that also works. But here I looked at the maximum, at the slope at TC, and that gives us an estimate of 1 over nu, which I call 1 over nu star here, and then it converts, and this should be 1, and it looks very good. But this is very noisy for big systems because it's a derivative, so it's more noisy than the quantity itself.
And yes,
Yeah.
about this m to the 4, I'm still confused a little bit about the critical point.
Second.
This m to the 4 thing.
Yeah.
If the order parameter has, say, dimension 7, I'm afraid it's not convergent.
It does rely on the dimension of the order parameter.
It doesn't, because if you in the critical point, Max told me that this should be interpreted as an integral of m.
Right.
So if m has too large scale dimension, it doesn't make sense to do this.
Okay, I guess that can happen. But are there such cases where the exponents are?
Yes. Like for instance, there is this bizarre thing that's called the monster CFT in 1+1 dimensions, where the lowest order parameter is scaling dimension 2, and then this integral wouldn't converge.
Right. Okay, but it will converge for finite size, right?
No, it's a UV derivative.
Yeah, it wouldn't tell you about the fixed point, universal.
Oh, I see. Well, okay, there are odd things, but normally this works. And if it doesn't work, I think we would see it, right? So I know many of you work on very exotic things. Maybe these will break down if we have some super exotic things, but let's see then. Okay.
Sorry, can I ask another question for the Binder ratio?
Yeah.
So previously you showed for the symmetry breaking phase, you approximate the distribution as 2 delta functions. But for the symmetric phase, you use a Gaussian.
Oh, okay, good point. Yeah. So you could also in the case of the ordered phase, you could keep these as Gaussians, but they are not actually very symmetric. But it actually doesn't matter, because if they are a finite distance away from zero, it will be completely dominated by the mean anyway. So the shape that would just cause some higher order corrections. But you cannot do that because this is centered around zero. So what's away from zero will always contribute, right? Yeah, that's a good point. Okay, so now what I discussed so far is more or less the condensed matter sort of general way to look at this. Now I want to talk about it in some way that is maybe more close to what field theorists do, or maybe not. I'm actually not sure because I'm not a field theorist, but I want to express things using scaling dimensions. So if we look at some lattice operator O, and we look at it at 2 different points. Well, maybe I should set 1 to 0 and call the other one R. Here R means the distance between the two. So these lattice operators contain all field operators in principle that are consistent with the symmetry, right? So it's not like an operator on the lattice has only one scaling dimension, right? So you get a sum of many of them. So in principle, you could maybe imagine that you have some cross terms here as well, right? I mean, you have this contains several operators and this several, so you have cross terms which I don't have. My understanding is that in the CFT at least you don't get those because of the operator product expansion. So that's one thing. The other thing is, well, so when I talk about lattice operators and their scaling dimension, then we mean the smallest delta is what we call the scaling dimension. But there are always, it contains always many operators. Okay, so now let's look at the critical Hamiltonian. So let's say H0 is some Hamiltonian tuned to the critical point, or in a classical model I see it at the critical temperature. And now we add a perturbation. In this case, I just consider some, Ising model and adding a magnetic field, and I call that some n, okay? And then n is of course L to the b, so I can also write it like that. So now if you go to RG, which probably people here know much more than I do, the basic thing is how the free energy density scales, and now I write it at finite size. So we have this thermal field that we drive the transition with, and now we can also add this external field, and that corresponds to some scaling dimension y. So now let's just look at the singular part of this is the singular part, right? So we can also look at, there's also some regular parts that I don't consider. So we can Taylor expand at the critical point, in the absence of the field. Okay, that should just give us that, but we have L to the minus D. And also we could just look at it, from the StatMech perspective, what is the free energy density, well, that means that if we go from this and just to look at this is the order parameter of the transition, so that has some scaling dimension minus delta. So we can say, well, if we do actually break the symmetry, it should have that form. So if we put all these, these two together, we can see that the y here has to be d minus delta. So I guess this is just some hand-waving derivation of what everybody knows. So now we can say, okay, what does it mean that the perturbation is relevant or irrelevant? So it has to do with, when we add our perturbation, does the effect grow with the system size, or does it decay with the system size? And now we should look at this in this scaling form here. So this again should be an analytic function. So if this argument vanishes, we should, well, that means that the effect goes away, right? So that means that the perturbation is relevant if y is greater than 0 and irrelevant if it's less than 0. Okay, and if the perturbation is relevant, we know that we flow away from the critical point, but of course we don't know where we go. We go to some other fixed point. Okay, now, let's look at the Ising model again. So I want to talk about symmetric and symmetry breaking fields. So what I just talked about was adding a magnetic field which breaks the symmetry, right? But if you look at zero field, so what do we do then? We tune the temperature, of course. And the transition is caused by the competition between the energy, the internal energy, and the entropy. So the temperature is our field, and how should we understand that? Well, at least in condensed matter, when we do StatMech, we keep the temperature there. We don't think of the temperature as part of the Hamiltonian itself. So when you change T, you see that it's sort of changing your energy, and the energy is the conjugate to the temperature. So what we have to ask, if we would like to see what the correlation length exponent is, in the sense that, let me go here, back here. So here I looked at some form like this, and now I'm talking about this argument here. We are changing the temperature. Okay, so then the scaling dimension is this one. This 1 over nu is d minus delta. So that 1 over nu is y, right? So if we change the temperature and we ask about the scaling dimension, well, that gives us the correlation length. That's the scaling dimension of the energy itself. So if you look at correlation functions of the energy, it should decay as R2 minus 2 delta, and that delta naught should be related to the correlation length exponent in that way. Okay, so this is a symmetric energy, or T, whatever you prefer, is a symmetric field in the sense that, well, we don't change the symmetry of the system when we change the temperature. Okay, but you can also do the field, the magnetic field, and then we do change the symmetry, right?
So is this energy density correlation?
Yes, it should be. It doesn't really matter. I mean, you just get a pre-factor if you take. Well, no, it doesn't. It depends on what you look at. If you look at it as a function of R, it wouldn't really matter, right? You just get a big, pre-factor that depends on N if you take the full energy. Well, no, sorry. Of course, it has to be the density because you look at it at some points, right? I was thinking about total E squared, which we actually can. Okay, so in the case of the magnetization, if you look at magnetization correlations, we get another scaling dimension, right? And that's related to another correlation length exponent as well. And again, this is the trying to connect the languages. So in condensed matter physics, people write this correlation function normally with this exponent, where eta is the anomalous dimension, right? So this scaling dimension m is related to eta in that way. I'm just, probably everybody knows this, but I just know from experience. Sometimes when I talk to field theorists and I mention, exponents 8, and they don't know what I'm talking about. I'm not claiming that applies here, but it has happened to me. So the interesting thing, of course, is that normally normal critical points only have one relevant symmetric field. So you tune the temperature, you can tune other things. There should only be one relevant field. But we can have multi-critical points that have more than one. Okay, let me clarify this a little bit by again looking at the icing model. But now let's look at adding a next nearest neighbor coupling. Okay, these green lines here. So, okay, the normalizing model is just the J term. So now you can ask, if I add this second neighbor term, is that a relevant perturbation? Okay, and now I would like to ask you, so if you believe it's a relevant perturbation, raise your hand now. Okay, a couple of hands, and if you believe it's irrelevant, raise your hand. And if you don't know, raise your hand. Okay.
I don't think it's a correct question.
It may not be the right question, yeah, so let's see. But again, I'm telling you because this is some sort of pitfall maybe that you can end up with. So, let's look again at the scaling down. Let's really do the calculation and compute the scaling dimensions. So here, I want to have an operator which is, sort of obeys the rotational square like this symmetry. So I put the icing energies in a square. That's this J1, J term, and the K term. I put these two interactions, and those are my operators. And then these are the correlation functions, which I actually computed yesterday because I wanted to show this. And you can see that we expect them to decay like 1 over R squared, and they both do. So this is our relevant operator, and now that seems to be also a relevant operator. Okay, so why is it like that? Well, because if you look at the case diagram, okay, this is the normalizing critical point, but now I put K here. And you can expect that if you add more ferromagnetism, Tc will go up. So when you are adding K, you are going left or right here. So you do go from the disordered phase into the ordered phase. You should expect it to be relevant in that sense. So if you really want to maybe see if it's actually relevant. I think this is maybe what Max is hinting at. You have to sort of add, subtract some J from it so that the average, effective coupling is the same or something, so that you really stay on this line. Or another way to say it is to make this line flat. Is that what you have in mind? Right.
If you insert a generic operator which preserves symmetry, you would expect that it will have, because you have to go to a basis where you decompose it into operators which scale homogeneous. Mm-hmm. So a generic operator will have all operators.
Yeah, exactly. So I'm not saying that this is anything mysterious, but again, the reason I'm telling you some of these examples is that these analogies to these will come up when I talk about deconfined criticality, and then it's actually, you will see some mysterious things exactly related to what you just said. But yeah, this is pretty natural. But at least in the condensed matter physics community, if you just ask people, most will say, K should be irrelevant, because we know that it doesn't change the universality class. But if you actually do this computation, well, yeah, since it contains all the fields, it will be relevant. So I think you can say that it's relevant, but maybe in some sense it's not the right question. Let me show you some other cases. Now I add these with different signs, so that's like breaking the rotational symmetry of the lattice. Then you see they both decay very fast, so these are irrelevant. And of course, in this case, since some of them come with minus and some of them come with plus, you don't change the average coupling. So here, TC, I think it's even follows from this that TC will be very, very flat as you go there. Okay, so this was a simple example, but it will be
So this is the dimension of some spinful operator of the CFT.
Say again?
This is the dimension of some spinful operator.
Yeah, it should be. Yeah, it should be exactly some. Well, yeah. The terminology used in CFT is still a bit confusing to me, but I think it corresponds to. It's not at least a symmetric operator.
4.4. The dimension should be roughly 4, right?
Say again?
The power should be 4.
Since I just did it yesterday, I didn't even have time to look it up. But and it may be that this is so you say it should be marginal.
I think it should be just stress energy tensor.
But I think if you take an IC model and you actually modulate the couplings, the universality class is the same. So I'm saying it should be marginally irrelevant. Or?
I think it's just a stress energy tensor, right? It's
yeah. So maybe it should be 4 exactly, but yeah, it doesn't look like it is. But again, I didn't do this as carefully as I would normally do because I just decided to have this yesterday. But I think it should be 4 exactly. Yeah, it's very possible. Okay, let me just mention that in these spin models, often we have a symmetry that helps, right? So if you look at the icing point, if you just want to go on this, so this is the first order line here, right? If you just want to go on that, well, we know that zero field does that, but we also know that the gas-liquid transition is described by the same low energy theory. So here, we don't have any obvious, symmetry breaking that we do here, and it's hard to. So the order parameter, of course, is the deviation of the density from the mean density. So that's a scale just like the Ising magnetization. So if we want to see this thermal field here, we would actually have to very carefully go tangentially through the point, which is very hard because we don't really know exactly where the point is. So if we go in some generic direction here, we get contributions from both the fields when we analyze data. So the gas-liquid transition is actually much more difficult like that because if we just go like that or like that, we actually go in some arbitrary direction and we mix scaling dimensions. Okay, so now let me come to quantum systems, and I guess I'm going very slowly, so I don't know how much time I've already used quite a lot of time. Okay, so let me actually skip this. I have an example from a quantum system as well, showing that we can extract the correlation length exponent from some energy-energy correlations, which people normally don't do. Normally people use these bin accumulant slopes and so on to get the critical correlation length exponent, because this decays so fast that it's actually very hard to get good data, statistics, because the decay is so fast. But anyway, we can check that it actually works. Now let me talk a little bit about emergent symmetry. This will come up when we talk about the Deconfined criticality as well. And let me do the example of 3D clock models, which are quite interesting and useful in this regard. So we take the XY model, the O2 model, and we add cosine Q theta. So for example, Q equals 6, you have 6 favored directions. Actually, we can also consider what's called hard clock models, where we only let the spin point in these directions. This will be the soft clock model, where we just have a potential favor in some directions. Okay, so now it turns out that this, if you analyze this clock term, it's what's called a dangerously irrelevant perturbation, if Q is large enough. Q is 4 or larger, it turns out. So that means that it doesn't change the critical point, but of course it changes the symmetry breaking of the ordered phase, so it's relevant in the ordered phase. And that means that in addition to the correlation length, governed by the exponent mu, which is the 3D xy exponent, there's another length scale which is even larger, which tells you that okay, within that length, it looks like the system is U1 symmetric. And that length scale diverges, eventually it's U1 symmetric. So this is quite a long story, but numerically it has been quite hard to analyze this. So there's a lot of preset papers. So basically, just very superficially, what happens if you are so this lambda is sort of the strength effective during RG of that clock perturbation. So if you sit at the critical point, you flow to some fixed point, which is the 3dxy critical point. So this becomes irrelevant in the case of array.
What Q?
So again,
what is Q in this diagram?
what is
Q.
Q, the number of clock states.
It's this cosine.
Oh, this Q. Okay, that Q. That's yeah. So let me say what fixed points. You have the xy critical point. You have the paramagnet, this ordered phase. You have an ordered, O2 phase, xy symmetry breaking phase, and you have the zq symmetry breaking phase. So eventually, in the ordered state, these break zq symmetry, so they have to flow there. But if you are close to the critical point, this second length scale is very long. So what that means is that this perturbation is almost irrelevant. So it starts to flow towards the U1 symmetry breaking phase before, at some lower energy, longer length, it starts to flow to the clock form. So if you think about in this lambda here, I call it lambda Q. As you go into the critical phase, it's relevant. Okay, so that means that this flows up. But there's also this irrelevant part. So if you sit exactly at the critical point, it decays away. So this one can.
This is a plot for Q equals 6.
Well, this plot is just a schematic, right?
For which Q?
Well, any Q above 4 or higher.
4 or higher.
Yeah.
For Q equals 2, you go to 2 Isings? Like Isings
So
plus
for
Isings.
Q equals 3, it's the same as the plots model.
That's 3D.
Oh, no, it's, well, it is, but it's the first order transition, I think, yeah. Okay, so now let me show you how we can observe this in simulations. So, again, we simulate this model, and we have the order parameters, with magnetization as mx and my. And from the global mx and my, we can get a global angle theta. Okay, let me show you some histograms of this mx and my collected in a histogram. So this is for the 8-state clock model, and it's a small system. But you see that this histogram looks completely like a ring. So it looks like it's looks like it's U1. It looks like it's for the XY model. And this is the radial distribution here. Now, if you go to the same temperature, so this is slightly below TC. If you go to the same temperature but the bigger system size, now you see that we have these eight small islands here. And that means that L equals 4 was below this second length, which tells you when the U1 symmetry is violated, and here it's about that, so the symmetry has been violated.
Sorry, what are you simulating? The first soft clock model?
Yeah.
Right? And H is what in dimensional?
Okay, I think H was 1 here.
Okay, order 1. Okay.
Yeah, it doesn't really matter. You can take the hard clock model, which corresponds to infinite H as well. That also works.
And it will again. How can it have a U1 distribution?
Well, because when this is like coarse graining, right? You don't look at just one spin. You look at a bunch of spins, and then you can have many more angles, and that's how it works. So we can quantify this by this angular order parameter, which will be essentially 0 here. But because I put the same Q here, it will pick up and give positive contributions for all of those. So that we can do, and this is from a more recent work. We can make a sort of phenomenological orgy diagram where we have the bin accumulant on one axis. So then we know that we have points, this axis corresponding to fixed points. and then we can use this order parameter as the proxy for the field strength. It's not the field strength, but it's the effect of that. So then we can do different values of the temperature and follow how this goes with the system size. And you can see if we are below TC, it happens exactly like in that schematic or the flow diagram, that you start to flow so that this becomes smaller and smaller with the system size, and you start to go to what looks like U1 symmetry breaking phase, but then it turns up and it goes very large. So here you see that it goes to 1 eventually. So one can analyze these in different ways and get different information. And now, if you write down the scaling form for this order parameter, it again is governed by some, a scaling dimension. Now it turns out that this is a global quantity, so this, this is not governed by by delta. It's governed by y directly. I can maybe mention that in more detail, but it's because it's a global quantity, so there's no dimensionality, spatial dimensionality or length coming in there. Okay, so then you expect this to be governed by some exponent that I call nu prime q, and that should be related to this scaling dimension. Now this is the way they are related, but this has actually been quite controversial as well, how exactly those are related. It's not a trivial thing. I think it was first shown in a paper by Sandvik and Chubukov in 1989 or something like that. But later people proposed that it's wrong, and then other people again showed that it's correct. So what you can do, you can actually directly extract that exponent if you go below, a little bit below TC, and you get a sort of data collapse, because below TC eventually this is a dimensionless number. It should be around 1 eventually, so I can extract those. Let me just show you how and this will be maybe the last thing before the break, and I want to show it because when we come to the deconfined critical point, we have a potentially emergent SO5, and we analyze that in pretty much the same way. So if I go to to the critical point, so this order parameter will decay to 0, and u will go to the critical value. But now I'm just interested in how does it decay to 0. And these are results for different clock models. Q equals 4 with a soft field, and Q equals 5 with hard and soft, and Q equals 6 with the hard clock model. And we just say, okay, we sit at the critical point, so these are absent, and then we Taylor expand those. So eventually, it should just be, this is negative, it should eventually just decay with this leading power law. So basically we're just getting this from these slopes here. So you see when Q is large, the decay is very fast, and the slope gives this scaling dimension. And when Q is 4, it's almost not irrelevant. The decay is very slow. So this is just a table showing that we get, with this way of doing it, which is not the way people normally do. Normally people calculate these scaling dimensions from the model without perturbation, just computing correlation functions corresponding to this perturbation, like I showed before, and get the scaling dimensions from there. But in some cases we have the problem, or it's just the case that the model itself contains these symmetry breaking perturbations, so we cannot study the model without those. So then we can look at, okay, there is something that violates some symmetry, and we can look at some quantity that picks up this violation and see how some suitable quantity decays. So this is just to show that actually does work. So it should also work what I show you after a break when I start to talk about deconfined quantum criticality. So I think now this is a good time to take a break, but maybe there are more questions before. on this introductory stuff.
Yeah, just in the phase diagram, when you look at X and Y, they were two fixed points, weren't they? No?
I'm talking about this one here.
Before that, you had like a diagram of flows.
Yeah.
Yeah, that's
Yeah.
right. So is X and Y, are they like fixed points there?
Okay, so this is the fixed point of the disordered phase, right? That must exist. This is the fixed point of the XY model without the clock term. This is the fixed point of the ordered, XY model, the O2 fixed point. And this is the fixed point corresponding to clock symmetry breaking, where the magnetization point in one of those.
Q is like a trivial fixed point?
So,
is Q trivial?
well, in some sense, yeah, because in the same sense that if you have an XY model, Y is trivial.
There are no couplers, sorry. Yeah. But X, so the only way to get to Y is through X. So you cannot, if you start your flow elsewhere, you cannot get to Y. You have to first arrive, only. So
right, exactly. So you only get close to Y if you are very, very close to TC, right?
Yeah.
And again, it's because you have two length scales let's see, you have two length scales. Well, I guess I have it here. So the correlation length, and then you have this, the length scale setting the crossover between U1 and the ZQ. And this one can be much larger. So that's why you have this long portion of this flow where it looks like the system orders like an XY model. Like if you look at this, you say, oh, this is the XY model in the ordered state. But then when you go to bigger sizes, the size, which is what you coarse grain over, has become larger than that length. So now, Z8 in this case feature.
Is Q what is called the same what is called discontinuity fixed point?
Called what?
Discontinuity fixed point? I don't know if
I
anybody
never heard that term, but it's very possible. Maybe somebody else knows.
They're reading too much stuff from the 70s.
Right. Yeah.
Can you show the definition of phi Q again, please? Of phi Q?
Yes.
Yeah, you just had it actually.
I think it was here.
So if can I read that in terms of some correlation function?
Well, so, there are actually other ways to do this too, but we just get these from basically this histogram. So each configuration in the simulation gives a point here, and we extract the angle from there. So you can think of it as integrating over, this distribution here. But one can also, look at, actually when I talk about SO5, I will also talk about some other quantities that correspond to including some power of n here, which would more emphasize out here. Well, here doesn't matter because there's no weight in the middle, but yeah, you can look at. There's no unique way to do this, right? You can look at various things. Yeah.
I think a somewhat related question. What is the physical intuition of phi Q? Like, what is it trying to measure?
What is
the expression? Like, what does it mean?
You mean this expression?
Yeah.
Well, okay, so if you just integrate cosine and you have a completely uniform distribution, you get 0, right? And now if I have a Q state clock model, eventually I get, Q equally spaced islands here. I mean, they're a little bit dim, but I think you can see them. So if you put Q here, then each of these islands basically, give you +1. So if you have, 8 delta functions here, this will be exactly 1. So this picks up the deviation from completely, U1 symmetric distribution.
So if the U1 symmetry were to emerge, this would be 0, right?
Yeah, so this is called, emergent U1 symmetry, right? Because the model itself doesn't have U1 symmetry, it says ZQ symmetry. But because that perturbation is irrelevant at the critical point and what's called dangerously irrelevant in the ordered phase, when you coarse grain over some large patch of the system, the symmetry emerges until you do it on too big a patch. So at the critical point, both these length scales, both length scales go to infinity. So at the critical point, you have perfect U1, and that's why it's in the 3dxy universality class.
So maybe this is a good time for us to have the break.
Yeah, exactly.
Okay.
That was the point. Because now next topic will be what the title of my talk is.
Very good. So we'll reconvene in exactly 7 minutes following
Chairman.
Okay, I'd love to read it.
What is it?
It just came out.
Yeah.
Okay.
I'll just stand here until you get in.
Like us having simply breaking reservation that's not multiple operator but it's relating to free energy, that's why we have like slightly different scaling. So you don't connect the control line and add the symmetric breaking reservation, the scaling dimension change is a different like some operator does not participate the other
It's participating.
not just like participate
Participate.
in the whole like culture.
You can say so. Well, it depends actually. Are you talking about the equivalent, right? So actually, it depends on which studies you are, because you are in the scenario where you're talking.
Okay.
These are relevant.
Okay, Anders, ready?
Yeah, I'm ready.
Okay, cool. Okay, let's get started again. Thank you, Anders.
Okay, so
Yeah, okay.
so now the actual topic of my lecture, Deconfined criticality. So this is basically starting with the Heisenberg model and adding some other interactions with the same signals and trying to destroy the long range antiferromagnetic order. And then what we get, we could get numerous things, but it turns out that one interesting thing that we can get is spontaneously dimerized state, where these orange blobs here mean basically singlets. So this is a cartoonish picture of of a columnar valence bond solid. So this transition has been investigated since a long time back. And in 2004, there was a new aspect of this by Sentel et al. Saying that this transition should actually be generically continuous, which is unlike what one would expect from Landau theory. If you just write down some theory with two order parameters, you would typically not find that both order parameters vanish continuously at some point. You would find some other phase in between or some coexistence phase, or you would have a first order transition between the two. So this caused quite a lot of interest and controversies as well. So the thing is, I'm not a field theorist, so I will not even really discuss the field theory behind it. But I can just mention that it's the CPN-1 model, and they studied it for SUN for large N, and in that limit it becomes almost like some kind of mean field theory, and then one can do at least to some extent 1 over N corrections. So in that limit, it's I would say quite clear that you have this scenario, though I think the VBS is basically also gone for large N. It becomes maybe not maximum. Is the VBS even there in large N?
Yeah.
It's just that it has some very large exponent of the VBS correlator, right? So the correlation became very fast, but the VBS is still there. Yeah, of course. Right, so I should mention to those who don't know that there are at least two experts here, Max and Michael as well, have also worked a lot on this deconfined criticality, so they can correct me when I go wrong, and others as well probably. Okay, so it was always talked about generic continuous transition, but not really proven in the theory. But one should mention that generic continuous doesn't mean that it's always continuous, right? I mean, you can also have this kind of scenario if you just take some model with two parameters. Maybe you have a critical line here ending at some multi-critical point and then triple point, whatever, and then it's first order like that. So when we do numerics, if we are unlucky, we just look at that side and we don't really look at that side. So that's one of the difficulties or controversies here. So, yeah.
For the numerical study, which large N have people studied?
Okay, so when I say large N here, I mean in the theory, right? So people can do compute some exponents using 1/n expansions and so on. But one can also actually do numerics for lattice Hamiltonians for large N. So I can say something about that on the next slide. I was not going to really talk about it, but I can make a comment about it. But those comments, they were referring to actual analytical calculations, which probably maybe in some cases require some numerics as well to do some integrals or whatever. Okay, let me talk about the kind of models we have been using for studying this, transition between these two states.
But before you continue, so in numerics, what models are these in particular? Is it large spin? No, not large spin. It's some SUN.
You mean now in the theory or in the numerics?
Yeah, in I mean Hamiltonian. What do you put on sites? It's some
okay,
kind
so
of
this
SUN
is what I'm going
spin?
to talk about now, right?
Okay.
So I don't know if this answers your question, but the models we are studying are square lattice models. We start with the Heisenberg model, but let me express the Heisenberg model as a sum of singlet projectors. So then we can, okay, now we know that this model has long-range antiferromagnetic order. That's what I showed you in the beginning. Now we want to put in some other interactions that kill that order. And of course we could put some frustrated interactions and so on. But the problem is we want to be able to do large-scale, quantum Monte Carlo simulations, which we cannot do for, let's say, the most natural models that you would write down. So the model I've been studying for too long now has the Heisenberg model and then these products of singlet projectors, and one can do any number of these projectors in products, and we add all translations, rotations, and so on. So we still have the full square lattice symmetry. So these one can do with QMC simulations, no sign problems. But these clearly, maybe clearly compete against the antiferromagnetic order because it favors these correlated singlets, and of course singlets don't have any antiferromagnetism. So you can imagine that when I add these with a negative sign, that we would actually kill the Nell order and go into columnar VBS, and that turns out to be the case.
But here you're just talking about n equals 3.
Okay. So then, so there was the expression of what SUN. So one can actually easily generalize these to SUN as well. But and actually in the same sense that was done in the theory. So you do SUN on one sublattice and the fundamental representation and the conjugate to the fundamental on the other sublattice. And that has a very simple, there's a very simple way of generalizing.
So that leads to the phase transition that is known theoretically for large N?
Yes.
But doesn't that break translation symmetry here now? It's SUN fundamental and it's conjugate.
Bigger lattice.
Oh, and then you.
Bigger lattice concept.
Yeah,
I would think that there's Lipschutz-Matisse theorems which would be violated. And I thought this was crucial for this system.
I think there is some kind of isomorphism between N and N bar.
I see.
So you actually look at translations.
Up to maybe charge conjugation or something, I'm guessing.
Yeah, so this was the kind of model that Sophie's actually considered also a long time ago in just the Heisenberg model. So it turns out that the Heisenberg model itself, if you go to SUN, it will have this kind of columnar EBS state for n larger than 5 and larger.
So numerically, which N have been studied?
Yeah, so basically we can generalize this JQ model to SUN, and that has been done.
Has it been numerically studied?
Yes.
Yeah.
In the continuum language, this field theory has a gauge field. It's a U1 gauge field coupled to n fundamentals or something. So the gauge field here is emergent. It's like
it should be, everything should be emergent here. That's the interesting thing, I guess. That in principle, if this is all true, we can study emergent gauge fields and fractionalized excitations and all that. This kind of model we use to test predictions from the field theory. But in fact, as we have been doing this year after year, now we start to see that maybe the original theory is not really applicable here, but it's still quite controversial. So I hope to tell you what we have been doing. But a lot of what I will show is actually not even published yet. And if somebody has some ideas, about the difficulties or mysteries that I will present, that would be very welcome. I will not talk much about experiments here, but in principle one can use these to make some contacted experiments as well. So now let me just show some basic results convincing you that there is a phase transition here. So we already talked about the Nell state and its staggered magnetization that we use as the order parameter. Now we also have to define an order parameter for the VBS, and there are many ways to do that. Here is one example where it's a spin rotationally invariant operator that we use. So this is just basically, in some sense, measuring the singlet density on the columns or on the rows, and adding them up with the plus or minus sign to detect that kind of order. So this is a two-dimensional order parameter. So now we can use bind equivalents, and they are again defined such that they will be 0 if there is no order of its type, and 1 if there is order of its type. So let's look at what we get. Again, these are results for different system sizes up to 512 square. And you can see that these curves develop eventually into step functions. And if you just and by the way, the step is at the same place as far as we can tell. So that means it's really direct transition, no coexistence or no other state in between. So we use the kind of crossing point analysis that I told you before.
Sorry, under L512.
Yeah.
How did you simulate that?
Using a lot of computer time for many months.
What is the VBS symmetry here? Is it Z4 or Z2?
Z4, because you can shift these and you can rotate, so you have 4 states, and the way they fluctuate to each other, you can see that corresponds to Z4. So we can extrapolate the critical point. We can use different types of crossing point analysis. So this looks, at least superficially like a continuous transition, right? But there are quantities that look like they shouldn't look like in a continuous transition. But everything that people showed up until recently was sort of looking a bit ambiguous. You could say, well, maybe it's still continuous. So let me show you the very latest results. So now, to detect long-range order, we can also look at not just the order parameter square defined on the whole system. We can also look at the long-distance correlations. So when I showed you results for the Heisenberg model, I also showed that. So the long-distance correlation function should go to the order parameter squared. So let's look at, so we have determined the critical point to quite some precision, but there's also still some uncertainties. I'm showing results for 3 nearby values of J. Here Q is 1. And this is the long distance spin correlation function. This is the long distance dimer correlation function, and again it's as a function of the inverse system size. So if this goes to 0, that means that it's a critical point, right? And then this power law should correspond to what a scaling dimension. Okay, so it looks like that, right? But now let's blow the scale up a little bit. So now in the previous slide, let me go back. You see, this started at maybe L equals 12, I think is the smallest one, and the largest was actually I think 448 here because 512 may not be quite converged. So now the smallest one here is 128, and this actually is this largest is 384. I've used different methods, different sets of data and so on, but I think this is 384. And the point is we also need very small error bars. So that means very long simulations to really see this. But now I think nobody would really be very confident to say that this vanishes. Right? It looks really more like it goes to 0 with a leading linear correction, which is exactly what you expect if you have some broken continuous symmetry eventually. Okay, so that's the spin order parameter. This is the dimer order parameter. Also seems to not go to 0. So this model really is, it does not sit at a critical point. Let's go to the JQ4 model. So I showed you these different Q terms that we can have. So the index here is how many of these singlet projectors do we have lined up in our operator. So here it's 4 of them. And then again, you can do simulations, find the critical point, do some calculations of correlation functions close to those points. And now you can see that, if you look at the values that this extrapolates to, that this seems to go to a bigger value. If I look at the black points here, you see that they bend in such a way that you can believe that, well, that will clearly go to a non-zero value. If you look at the black point here in the dimer correlation, well, that seems to go to 0. So that means that the black points are in the AFM phase. With the red, it's the opposite. The red is in the VBS phase. And this is very sensitive to the exact value, so we can, each value of Q here takes a long time, so we cannot do everything we would like to do. But it seems like the actual transition point is between those, and they both extrapolate to non-zero values. So that means that there's coexistence of these two order parameters, but only most likely at one point. There's no coexistence phase. They only coexist at one point. That means the first order transition. So these
So these are correlators of order parameters at opposite points of a cylinder, right?
That's right.
And you're taking, so you're just saying that they should go to a constant if you're in a broken phase.
That's right. Okay. That's exactly right.
But on the filtering, if we think about the filtering model with U1 and scalars, for large n it's a second order, and for n equals 1 it's second order.
Right.
That's the particle vortex model.
Yeah.
So it seems natural that for any n it would be second order. If it's second order for n equals 1, second order for large n, well, how does it make sense?
You would have to ask Sentinel at all why they would, but that's the argument. Right?
What?
Why? Well, again, I'm not a field theorist, so I cannot say why they. I think actually what I think it is, but they did large n.
The large n was done in the 70s. What does it have to do with center? Large n was done by Halperin, Lubensky, Ma in 75.
Yeah, I know that they
But I think they computed also relevance of monopole operators, right?
He has Z4, so it's only a monopole of dimension of charge 4.
Yes.
It's irrelevant to n equals 1 because it's a superfluid. N equals 1 is a superfluid model. And
but I think those long time ago people also didn't do n equals 2, right?
How do you know it's monotonic? I mean, it could be relevant for n equals 2.
I know it's irrelevant at n equals 1, irrelevant at large n. So most likely always irrelevant.
I think that was their original justification for it, right?
But this is not from the 70s. Everything I said is not from the 70s.
Yeah, the one over n was also not
margins known from the 70s.
Anyway, I'm not the right person to fight about whether this is correct or not, and in the end I will say that it's not quite correct, but at the same time, it's just an interesting question. If you even, okay, regardless of the field theory, it's interesting to know what happens when you destroy the nail border in a spin one half system. So you can just think of what I'm doing as that, and not necessarily that I want to defend some field theory or not defend some field theory, but we want to definitely compare with whatever predictions are out there, right?
Zohar, it's an experiment. I mean,
You
the
can think of
experiment
it
has
as
to
an
agree with
experiment.
the theory. If what you say is true, then it should be possible to.
And you may say,
Just the wrong lattice.
Huh?
I mean, a lattice could have a first order transition, but the fixed point could still exist.
well,
That's
I will get to that, so I think the fixed point exists.
Yeah, of course.
Yeah. Well, you say of course, but this is something a lot of smart people have been fighting about. So I suspect it's not exactly of course, but
Do you have a JQ3 as well?
yeah. So that's something in between.
We
I
even
didn't
see-
want to.
We see this fixed point in the bootstrap. The only contention I thought it was if it has SO5 or doesn't have SO5. And okay, but the fixed point we see it clearly.
I don't think that's true.
Yeah, but it's not.
You don't see it in the bootstrap.
Well, let me
There's some constraints from the bootstrap.
Let's let Anders continue.
Yeah, let me continue because I have a lot of results that touch on all these things, and I think you will be able to. I will be able to answer some of your questions, but let's see.
Before you continue, can I just ask a minor question?
Yeah.
Can you comment on the arrow bar?
The error bar they're not seen here because they're so small. I mean, I have plotted error bars here. I think in some cases maybe you can see some little thing there, but that's exactly the point, that to really see this, you have to have small error bars. Otherwise, if you just do a calculation for a few days, the error bar is like this big, you cannot say. So actually it's a really good point, and that's why actually this has taken a long time to actually come to this point, to be able to show you this kind of graph. Yeah.
And so would you say that in JQ4 it's quite unambiguous that it's first order, and
Yes.
JQ2 it's not quite clear?
Well, I think even, JQ2 until quite recently I thought, well, it's, maybe first order, maybe not, I don't know, but now I think I'm quite confident that this is first order as well. Okay, but that's not the full story.
Coexistence or not?
Say again?
One thing I didn't quite get. Over here you said it's first order. Here is it coexistence?
Well, first order means coexistence at one point, right?
No, yeah, so is it a phase or just a...
No, I think it's just at the point, but of course I cannot exclude that it's a super narrow phase. It's actually, also a possibility that it is that, but I sort of think it's more likely that it's just a first order transition with coexistence. When you do the numerics again, you don't break any symmetry or favor any phase from another, so there will be some tiny range where you can see both orders on finite size, and that range grows smaller and smaller as the size grows.
Can I ask a stupid question? I mean, Binder cumulants should develop this dip. But
Exactly. That's a good point. So if you have a first order transition, normally the Binder cumulants that I showed you, which look very nice, they should develop some dip here. Actually, they don't do that here, and I think that also has to do with emergent symmetry. So I think eventually, if it's first order, we would see a dip, but maybe we have to go to 1,000,000 squared. But because there is at least up to some large length scale emergent SO5 symmetry, I think that's why we don't see it. So you don't have a normal coexistence state. You have a coexistence state that corresponds to being able to rotate in SO5 space between the different phases. But I will get to that a bit later.
So if you're trying to detect a very weakly first order, you're saying that looking at correlators is more reliable.
It's better than looking at the total order parameter squared, at least, because it has if you look at the total squared, it has contributions from short distances as well, which partially masks the most sensitive point, right? Yeah. Okay, but this is far from the whole story. So some people say, oh, DQCB is dead, but people have suggested, non-unitary CFTs and things like that. But let me tell you about some exponents that I believe we can still extract even if it's a first order transition. So I told you about the slope of the Binder cumulants. Now we have two types of cumulants, but we can look at the slopes, and they should give us the exponent 1 over nu, which should be given by 3 minus the scaling dimension of the operator that drives the transition. Right now, what drives the transition? We are changing the ratio J over Q, so you can say that Q drives the transition or J drives the transition. So it's the scaling dimension of the J or Q operator at the critical point.
Question?
Yeah.
In Monte Carlo, how do you know the dynamical exponent?
How do we know what?
The Z, the dynamical exponent.
Oh, okay. So we have looked at that too. So we are pretty confident that Z is 1. We can calculate the scaling of the gas, for example, and various things. So as far as we can know, can tell, it's 1. I will comment a bit more on that in a moment as well.
You said it's coexistence, not critical point, so I got confused.
Yes, exactly. But we are now, you saw the extrapolated value is extremely small. So you can imagine at least if you sit extremely close to the critical point, then up to some system size, the system will still look critical. And if you are close enough, the criticality survives up to such long lengths that you can still extract the exponents of the critical point that you cannot quite reach.
So you're imagining that there are some other Q operators that would hit
exactly.
this point and you're very close.
Yeah, I will come to that. So that's exactly the point. That, look now, we look at the QQ correlation functions, these energy correlation functions. And we can look at them at the longest distance as a function of the system size. Or we can look at the large system and just look at the R dependence, and you see we get decays that are very consistent. There's not even like any major corrections apparently. But again, the decay is fast, so we cannot go to super long distances. But this scaling dimension to delta corresponds to 1 over nu being around 2.2. So that's drawn with this line here. Now, if you just do what I told you before, we look at the slope of the Binder cumulant, look at its size dependence and do some L2L analysis and so on, we can see that 1 over nu seems to go to the same value. So now we have complete agreement between the scaling dimension of the driving operator and the signal in the Binder cumulant as we approach the critical point. So those are two completely different ways to calculate the same, and they agree. So that must, I think, mean that we are close enough to the critical point that we can still extract some sensible exponents. And this is the value of nu. Okay, it's quite small. Now, an interesting thing here is that this violates CFT, a very general bound. So that naively would mean that, this is not a CFT. Okay, if you wait a moment, I will show you that we can have a way around that. But first, let me say a little bit more about the universality of these pseudo-critical exponents, because now I can do the same calculation in, for example, the JQ3 model, which is also quite close to critical.
Good question. The paper you cited about the bootstrap, didn't they used some scaling dimensions of a single monopole operator, which is also from the lattice. I mean, I don't know how precise these were in the paper.
They definitely made some assumption. One assumption was that there's only one relevant scalar.
I think in this paper it's only about the epsilon correlation function.
No, it's also about nu. In an appendix, they also talk about nu.
About nu?
The new critical.
No. So by epsilon I mean I mean this. Whatever, the symmetric. So it just says, I think the only assumption is that in the epsilon OP, epsilon appears.
Oh yeah. Anyway, we can discuss later, but that's a bound that seems to be violated. Anyway, let's look at another model. Let's compare JQ2 and JQ3. So if I take my correlation function, and let's say now from the previous result, I have a pretty good estimate of what delta is, so I can multiply that out, and it should then go to constant when 2 times delta has this value. Okay, so this is the same model as I showed you before, but now multiplied out, so it should go to a constant. Now this is actually a different set of calculations. I mentioned before that we can do calculations at finite t and let t go very low, or we can do ground state projection. This happens to be ground state projection, another way to sort of check consistency with our calculations. But you can see that this is consistent now up to the systems before the error bar becomes too big to say, well, this goes flat, so that's the correct scaling dimension. Let's look at the JQ3 model. So, in the same way as in the JQ2, for small sizes or distances, you have corrections. Here the correction has a different sign. Then this goes flat, but then it takes off. And when this takes off, that actually can only mean a first order transition. That's something you can figure out from these energy type correlations. So I find it quite interesting that this is not just a minimum, it's a very flat minimum. So I think that means that there is some criticality in the system up to with some size where you start to see the first order behavior. And that occurs sooner in the JQ3 than in the JQ2. Okay, so so the claim is broadly that we have weak first order transitions. We can also have strong first order ones, but when we have weak ones, we get some universality in the exponents we calculate. So we believe that that means that there's an actual critical point nearby that we haven't quite reached that has those critical exponents. Let me check the time. So okay, so for a long time we have known that there's emergent U1 symmetry here. So this is similar to what I told you in the clock model. Now we can look at dx and dy in the simulation and make some histograms, and they look almost perfectly U1 symmetric in the neighborhood of the critical point. But now let's see, when we do these JQN models with larger n, then the transition becomes more first order like. So what does the distribution look like then? Now let's look at an extreme case, the JQ6 model. And actually, let's only look at the Q6. No, sorry, not only the Q6. I'm getting ahead of myself. JQ6, so we can extract, again, some transition point. And now we can look at histograms like these, where one axis is dx and one is dy. But in this case, it looks completely different. The blob in the middle here corresponds to the AFM phase, where there's no VBS order at all. Okay, and then 4 peaks here correspond to symmetry broken Z4, 4 blobs. But this is in a very narrow range of points going across the critical point. And you can see there's one case here where clearly C5, so that means coexistence of these VBS and AFM phase. So this transition is super clearly first order, and clearly there's no emergent U1 symmetry either. So that's quite natural, right? If we have some emergent symmetry, it should be due to a nearby, at least critical point. And if we don't have that, we shouldn't have emergent U1. Now let me talk about emergent SO5. So in one version of the theory, it's basically constructed with SO5 symmetry, and there was some proposal that there could be emergent SO5. So let me show you some results from Adam Nahum and co-workers, where they looked at, they didn't look at the same JQ model I've been looking at, but they looked at a 3-dimensional loop model, closed-packed loop model, which actually looks very similar to the JQ model, because when we simulate the JQ model, we actually simulate the loop model, it turns out. But the difference in their model is that they made it explicitly Lorentz invariant. They made the space and time dimension exactly the same. So they have the question about z equals 1 that you asked about is taken care of. The because z equals 1 is built in their model. And in our model, if z is 1, it's emergent Lorentz invariance. So this is a very nice complement to our model, and it was within their model that they discovered SO5 symmetry first. Okay, so you can define a vector, 3 components of Nell and 2 components of the VBS. Yeah.
In their model, is the autosymmetry exact, or is it still Z4?
It's still Z4. Yeah.
Still Z4.
Yeah. Okay, so then the question is, if you do those order parameters and you have to normalize them so that they are on the same scale, you can look at histograms, and then they found, okay, this is 1 component of the VBS order parameter and 1 component of the Nell order parameter, and it looks rotationally invariant. So that could mean that there's, well, it should mean that there's O5, but it should be SO5 in the spin model. Now they also looked at some numbers to make things a little bit easier to analyze. So you can look at things like that, similar things as I used in the clock model. So if you have O5 or SO5, and if theta, I forgot to write it there, but theta is the angle between 1 component of the VBS and 1 of the Nell order. So it's just looking at 2 components. But if you have SO5, yeah, that you should have this rotational invariance in 2 dimensions. Now you can rewrite that in terms of powers of these order parameters. So these are some numbers that you now can compute and look at as a function of system size. So in particular, when they go close to their critical point, this is 0, so that is consistent with SO5. And then you can compute what these should be. For example, in the Nell phase, the value should be a different one, which they get. If you have U1, it should be another value, and if you have Z4, it should be another value, and all of them are realized here. So this was the evidence for SO5. And this is just some example. They have other results in the paper as well. Okay, so now let's look at that in the JQ model.
Sorry, can I just ask, did they get the same critical exponents like you?
Yes, that's in another paper. They have, I mentioned that when I mentioned our value for nu, that in the 3D loop model, they also get the very similar value of nu.
So it still violates the bound?
Yes, yes, exactly. So all exponents that we have calculated from the JQ and loop models, they agree very well. So now let's look at SO5. So we can look at the same quantities that they looked at with some definition of the magnetic and dynamic order parameter here. For the calculation, I want to use a diagonal definition, so it's a bit different from what I used before. But we can also use some symmetrized versions of these quantities, which in some sense can have some better behaviors. So they should basically give the same values if we have SO5 symmetry. These F and G quantities should asymptotically give the same. Okay, so this is quite old by now, so we have better data. But this is just again to show that this is for the JQ3 model. If we sit at the critical point, this starts to go very small, but there is some size correction, and that actually will be an important thing, because you remember when I talked about the clock model, I had a clock perturbation and I looked at a quantity that detects the violation of U1 symmetry in that case, and that decayed as a power law, and I could extract the scaling dimension. So likewise, if we have an emergent SO5, in the lattice model, there is something that violates the symmetry microscopically, but in the infinite lattice, that violation should go away, and that should be governed by a scaling dimension. So if we analyze this decay to 0, we should get the scaling dimension. And that was actually, for some reason, not done in this paper. They just said, oh, this is very close to 0, so it's SO5. And actually, they even cut this graph here. I think the smallest size is 20, and you see that the scale is quite large here. So it's they didn't actually compute the scaling dimension of the operators that violate the symmetry. So this is what we set out.
Can you go back to the previous slide? I thought you were mentioning that there there was it will go as you go to the larger system, it will go away from the critical point.
Yes, exactly. So eventually, we should see that in the SO5 indicators as well.
But in the slide after this is already like a massive system. So why?
Well, it's not that big. But let me show you some better data where we really analyze this decay.
We did 512 in previous slides.
That's true.
This is.
So that's also in this loop model they also went to very large system sizes. But
but it's a different model, and it's not clear how big
You mean how to compare the sizes?
Yeah, I think maybe it's not. Maybe they need to go into even larger sizes to.
Yeah, but I think the one thing is that their error bars here are big, so you will see some results that I show you in a moment, where we have small enough error bars that we can see some power law.
Isn't it surprising that they don't do better than you because they have Z=1 built in? So if we assume the fixed point is
yeah, so in some sense maybe their model is better to study the criticality, but I haven't seen any clear evidence that it is. But in some sense it's an advantage. But I think it's really nice to have both, because then we can, if we get the same exponents and everything, then we say, well, actually our model has emergent Lorentz invariance, so that's nice. Anyway, so let's look at these F and G quantities, and in this case, the decay power P, the delta should be 3 plus P, because if this decays, it means immediately that it's an irrelevant perturbation. So the dimensionality, is added to that. Okay, this looks a bit funny because the F and this is the F2 and G2 quantities have two different couplings, and they don't look quite the same. I think they should eventually show the same scaling dimensions. For some reason, this one maybe starts to get the same slope there. But look at the values here. They are very, very small, and this should basically be the same quantity that I showed you from Nahum's paper. Let's say 0.02. Now let's go to their graph. You see the scale here, you cannot really, you would not detect anything like that, any deviation from zero when you look at it on this scale. And anyway, this is has a non-ideal behavior, but let's look at this one. This is the F4 and G4, and actually at least one of them is negative, so that's the absolute value. Again, if as far as I can tell, they should be governed by the same scaling dimension. And it looks like they are, but eventually that turns up and that turns a little bit down. So it looks like, oh, it's becoming even more SO5-like. But actually it's not. So now let's look at the same things in the JQ4 model, which we know has a first order transition. Okay, this is for the F2 quantities. Actually, let me show this one first. So here you get roughly the same slope as before, but now you see that this quantity here really starts to dive down, and it actually changes sign and then comes back up again. And then it will not go to zero anymore. These will go to some, start to grow eventually, I believe. So that really means that here you can see the violation of SO5. And with that quantity is something like that. And now if you, remember what this looks like. Now I go back to this one. And it basically looks the same, but here we cannot reach such big system sizes where this would go negative and go back up. But already here we see the violation of SO5. But the violation is less than in the JQ4 model. So again, I think it's consistent with, we are not really quite at the critical point, so then we have to violate SO5. But probably the point that we cannot reach has SO5. Now let's see how much time I have left. Minus 1 minute. So I want to show one crucial thing here, which I think is maybe the most important thing. So let me use 5 minutes. So we basically think that we have a multi-critical point. So we have talked about the JQ model, but these Q terms, one can make all kinds of singlet projector combinations. So we can do this one, which we call Z. Okay, and now we can compute the scaling dimension of Z. Okay? So we imagine we add it to the Hamiltonian, but we sit at the critical point, or the near critical point, and compute the scaling dimension. Okay. Now, since these have some funny shapes, we actually pack them into a square, so that the operator that we correlate doesn't violate any symmetry of the square like this. Then we get some decays, and then it turns out that this one decays much faster than the correlator for Q. And now this is why I wanted to show you the Ising K scaling dimension, because as we discussed there, you would expect, if you just taken some operator that has all the symmetries of your original Hamiltonian, that it would contain all the field operators consistent with that symmetry. So this operator should contain the same scaling dimension, 0.8 that we got for that operator. But it doesn't really seem to have that. So there is something, I don't know if the amplitude is just so small that we don't detect it, or if there is something in the microscopic aspect of this operator that makes it not contain the leading symmetric operator. But that's what it seems to be. Okay, so if we believe that, then we actually have two fully symmetric operators under our original symmetries of the Hamiltonian, whereas the bootstrap bound that we violated assumed a single relevant operator. Yeah.
This is not the correlations are not staggered in system size in some way.
Okay, so they do have some even odd effect. So this is as a function of R for a big size, so they do stagger. And actually, for versus system size, I only did the even sizes because there's also some staggering in the system. Well, we will only do even anyway. I think I only did multiple of 4. Anyway, okay. Now, so for some reason that we don't understand, this Z doesn't seem to be contaminated by this scaling dimension, but most likely this one is contaminated a little bit by this other operator that has that scaling dimension. Probably that's why the transition is weakly first order, because there is actually another relevant symmetric operator. Now, there's some theory paper already discussing all this, and let me not talk about it, but if anybody's interested, look up this paper.
But then the claim that it's generic is false.
Yes, exactly. So our, by the way, let me, before I say that sort of big picture thing, in the Ising model, we looked at also this kind of next nearest neighbor interaction. Let me just show you what that does as well. So that one actually sort of contains both the scaling dimension of the order parameter, because it actually also detects the order parameter, which actually the Q correlator does as well. I just showed you results for even distance, for odd distance. I think for even, it actually picks up the order parameter. But this other decay, the fastest decay, is actually exactly consistent with what you would expect if you just take another generic operator that can drive the transition. So the Z operator seems to be really special in that it doesn't contain that. Okay, now this is sort of a phase diagram which contains multi-critical points. So let's say that we did this JQN models and where N, but if we want to wear something continuously and see if we make the transition more strongly or weakly first order, we can combine different Q terms. So this is the JQ2 model, but now we add a Q6 as well. And then we can look at the phase diagram in the plane of here, as a function of Q2, which is 1 minus J, and Q6. So we have a nail phase and a VBS phase. So this is basically the critical point we talked about before. And so now, as we follow here, we have a coexistence, regular first order coexistence state. And this is actually very difficult, but we have tried to extrapolate the order parameters and see if they follow a power law, and if we could possibly extract the negative value of Q6 where the critical point would actually be. And at least it's somehow consistent with the known exponents, although it doesn't look very nice. We are still improving this. But now the point is that the original model doesn't have SO5. It only has low 3 and the lattice symmetries and so on. So under those symmetries, it looks like we have two symmetric operators or charge zero operators, whatever you prefer to call them. But if we have emergent U1, then we should look at what are the symmetries of those operators under that symmetry. And then I think that if we want to go in this way, that's the way we go without violating SO5, although, because we have some higher order, perturbations, we eventually violate it. But ideally, this would be the SO5 line.
What do you mean, first order, right?
Yes, first order, but you can have, if you take a classical O5 model, as a function of t, you have a coexistence state, and that's the first order transition between, let's say, O2 and O3 if you have some perturbation.
Why would it emerge?
Well, it would emerge if there is SO5 on that point. Then if we wouldn't have any other symmetry violating operators, we would have SO5. But of course, in the lattice model, we do have, irrelevant, but still, dangerously irrelevant perturbations that would still, kill the symmetry.
They're not irrelevant.
Let's give an attention to Rabbit.
Yeah, so the point is that under SO5, I think this going in this direction corresponds to an operator that explicitly violates the symmetry. Okay, so this is pretty much what I want to say. Let me just quickly say that maybe we are here, but actually we also think based on some other papers that it's not even really a line of critical points within that this opens up into a spin liquid phase. But that's not easy to study. But we have we have examples where we can use DMRG and other methods to have a spin liquid between the two. So we believe that in principle we can tune models to go between these different scenarios, and probably what we have is just a multi-critical point. And that multi-critical point still is probably some kind of DQCP, right? Though I'm not sure how we should classify it.
By spin liquid, you mean U1 gauge theory with no monopoles?
I'm not really quite sure what kind of spin liquid it is even. People have studied frustrated models, and it looks like there's a spin liquid, but people are still, it's a gapless spin liquid for sure.
Okay.
But exactly what kind, we don't know. Now, I did have one other thing, but I will stop here. But I'm just going to, if somebody wants to talk to me in private, we have some results for entanglement entropy as well, where we have some mysterious depending on how we make the cuts, and maybe this is a bit related to what Michael Levin talked about in his talk yesterday, where he pointed out that there's some difficulties in making the cuts on the lattice and comparing with CFT. So I can talk to people in private if anybody is interested. All right, thank you very much, and sorry for watching.
Maybe we'll take one or two burning questions if there are any. There's lot of discussion already, so okay. So if not, then we convene at 2:30 today.